The cosmos operates on timescales that dwarf the human experience, rendering the life cycle of a star nearly invisible to a species whose entire recorded history spans but a flicker of the galactic clock. In the grand narrative popularized by Carl Sagan, if the history of the universe were compressed into a single calendar year, the entirety of human civilization would occupy only the final seconds of December 31st. Within this vast chronological framework, the laws of stellar evolution are generally regarded as immutable. Stars are born, they consume their nuclear fuel at a rate determined by their mass, and they inevitably descend into the quietude of stellar remnants. However, deep within the ancient, tightly packed clusters that orbit our galaxy, astronomers have identified a class of celestial anomalies that appear to have discovered a fountain of youth. These objects, known colloquially as vampire stars and scientifically as blue stragglers, represent a profound challenge to our understanding of stellar mortality. They are the stars that stay young by preying upon their neighbors, defying the actuarial tables of the universe through mechanisms of siphoning and collision that mirror the most dramatic themes of human mythology. These stars are not simply younger versions of their neighbors that formed later. In the sterile environment of a globular cluster, the gas and dust required for new star formation were stripped away billions of years ago. Every star in such a cluster was born at approximately the same time, meaning they should all show common characteristics determined solely by their age and initial mass. Blue stragglers are the glaring exception, appearing significantly more luminous, hotter, and bluer than the stars that surround them, effectively resetting their internal clocks. The Sandage paradox and the birth of stellar chronology. The scientific journey into the secret of the vampire stars began not with a high-definition space telescope, but with a perplexing observation made in the mid-20th century. In 1953, astronomer Alan Sandage, working at the Palomar Observatory, conducted a photometric study of the globular cluster Messier 3. This work was conducted using the world's largest telescope at the time, the 200-inch Hale reflector, a 530-ton marvel of engineering funded by a $6 million grant from the Rockefeller Foundation in 1928. The construction of the Hale telescope was an epic feat that took 20 years to complete, involving the casting and polishing of a massive Pyrex mirror at Corning Glass Works. The mirror itself was so large that it required a special rail trip across the country, watched by thousands of people along the tracks, and its eventual installation at Palomar Mountain was a landmark in observational cosmology. Sandage, a student of Edwin Hubble, utilized this instrument to peer deeper into the past than ever before, seeking to establish a definitive chronology for the stars. During his study of M3, Sandage observed that as a cluster ages, its most massive stars, which burn through their hydrogen fuel with reckless speed, are the first to exit the stable main sequence phase to become red giants. This creates a visible turn-off point on the Hertzsprung-Russell diagram, which astronomers use as a cosmic clock to determine the cluster's age. However, Sandage discovered a small population of stars that remained on the main sequence far beyond this turn-off point, looking like young interlopers in an ancient population. He dubbed them stragglers, because they appeared to be trailing or left behind by their peers who had already evolved into red giants. This discovery was a revelation in 1952, as it proved that stars do not move up or down the main sequence as they age, but rather move off of it. Sandage's paradox suggested that these stars had somehow gained a new lease on life, a concept that defied the established rules of stellar physics and suggested a much more dynamic and violent environment within star clusters than previously imagined. To appreciate the vampiric nature of these stars, one must first understand the standard life cycle they defy. As Neil deGrasse Tyson has articulated, computer models of stellar evolution function much like actuarial tables for stars, where a star's mass is the single most important factor in determining its lifespan, temperature, and ultimate fate. The relationship between mass and luminosity is nonlinear, following a power law where a star with only twice the mass of our Sun burns through its fuel more than 10 times faster. The stability of a star like our Sun is maintained by a delicate balance between the inward pull of gravity and the outward pressure generated by nuclear fusion in its core, where temperatures reach approximately 15 million degrees Celsius. In this high-pressure furnace, hydrogen nuclei fuse to form helium, releasing energy according to Einstein's famous equation of mass-energy equivalence. This process sustains a star for billions of years, but it is a finite resource. When the hydrogen in the core is eventually exhausted, the star's structure begins to fail, the core collapses, and the outer layers expand into a bloated red giant. In an ancient globular cluster where star formation ended 13 billion years ago, all stars above a certain mass should have already completed this transition. The blue stragglers, therefore, represent a biological impossibility in stellar terms. They are massive stars that should be dead or dying, yet they shine with the vigor of stolen youth. The longevity of a star is fundamentally a race against gravity. While a star can burn brightly for eons, its fate is sealed by its initial conditions unless something intervenes to change its mass. Blue stragglers represent that intervention, demonstrating that the actuarial tables of the universe can be cheated through interactions with other stars. By gaining mass, they effectively move back down the main sequence to a position occupied by stars that are billions of years younger. The primary mechanism identified by scientists to explain this rejuvenation is stellar cannibalism, specifically through a process known as mass transfer in binary systems. Most stars in the galaxy do not live solitary lives like our Sun. They exist in pairs or groups, often orbiting very close to one another. When two stars are in such proximity, their gravitational spheres of influence, known as Roche lobes, can interact in dramatic ways. If one star in a binary system begins to evolve and expand into a red giant, its outer layers may cross the inner Lagrangian point, where the gravity of the companion star becomes dominant. In this vampiric embrace, the secondary star begins to siphon material, primarily fresh hydrogen, from its evolving companion. This influx of new mass increases the recipient star's core pressure and temperature, effectively restoking its nuclear fires and causing it to appear much younger and more massive. Meanwhile, the donor star is stripped of its outer layers and vital energy, eventually being reduced to a hot and dense stellar corpse known as a white dwarf. This confirms that the blue straggler's youth is not inherent but stolen, an artificial extension of its life cycle at the cost of its companion's existence. Astronomers have found that these cannibalized stars are common in many clusters, serving as a primary channel for blue straggler formation. Evidence for this vampirism is also found in a subset of stars called blue lurkers. These are stars that look like normal members of the cluster, but are spinning suspiciously fast. In the M67 cluster, researchers used the Kepler Space Telescope to find stars rotating in just 4 days, compared to the 30-day rotation of a typical Sun-like star. This rapid spin is a telltale sign that they have absorbed material and angular momentum from a companion, lurking in plain sight until their rotation gives them away. The theory of mass transfer was a hypothesis for decades until recent forensic evidence provided the smoking gun. In 2024, a team of astronomers from the Indian Institute of Astrophysics used the AstroSat Space Observatory to analyze a star named WOCS 9005 in the M67 open cluster. Using spectroscopy to disperse the star's light into a chemical barcode, they found that the atmosphere of this vampire star was rich in heavy elements like barium, yttrium, and lanthanum. These elements are not produced by the normal fusion processes of a star like our Sun. Instead, they are the hallmarks of the S process, or slow neutron capture, which occurs only in the deep interiors of highly evolved asymptotic giant branch stars. During this process, seed nuclei like iron capture neutrons at a rate slow enough for beta decay to occur between captures, moving the nuclei along the valley of stability toward heavier elements. Because WOCS 9005 is not an AGB star itself, the presence of these elements on its surface is definitive proof that it recently ate material processed by a companion star. This barium enrichment represents a chemical imprint of the theft, showing that the star siphoned an enriched atmosphere from its neighbor before that neighbor died. The study of WOCS 9005 marked the first time a barium blue straggler was identified in M67, linking the star's youth directly to its cannibalistic past. The S process is responsible for creating approximately half of the atomic nuclei heavier than iron in the universe, and its signature in blue stragglers allows astronomers to trace the history of mass transfer in binary systems. By measuring the abundances of barium and other heavy isotopes, scientists can calculate how much mass was accreted. In the case of WOCS 9005, an estimated 0.5 solar masses. This chemical forensic work turns the light of these stars into a record of their long-vanished companions. While binary mass transfer explains many vampire stars, it is not the only way to cheat the clock. In the incredibly dense urban centers of globular clusters, stars are packed so tightly that they literally bump into one another. In clusters like 47 Tucani, the central density is more than 10,000 times higher than in the local vicinity of our Sun, making direct stellar collisions a frequent reality on a cosmic timescale. When two stars collide, the result is a massive and highly turbulent merger, an event compared by astronomers to a head-on wreck between two tractor-trailers. Unlike the slow siphoning of mass transfer, a collision involves a violent and complete mixing of the hydrogen fuel from the outer layers of both stars into the core of the new, single object. This rehydrogenation allows the merged star to begin its life as a massive blue star with a fully restored fuel supply. These dynamical blue stragglers are almost exclusively found in the very centers of clusters where the gravity well is deepest and the crowding is most severe. High-resolution observations from the Hubble Space Telescope have confirmed that stars in these dense cores are rotating extremely fast, with one star in 47 Tucani spinning 75 times faster than the Sun. This rapid rotation is a direct consequence of the kinetic energy deposited during a collision or a violent binary merger. The existence of these collision products explains why blue stragglers are often found in the most chaotic regions of the galaxy. In these environments, the proximity of stars is so great that they are prone to capture each other or simply merge through brute force. This path of stellar demolition creates some of the brightest and most massive objects in the cluster, ensuring that even as the general population fades, the core continues to shine with the light of these rejuvenated giants. One of the greatest challenges in studying vampire stars is that they often hide in plain sight, their light masked by the glare of thousands of bright red giants. However, because blue stragglers are significantly hotter than the surrounding red giants, they are exceptionally bright in ultraviolet light. Using the ultraviolet-sensitive cameras on NASA's Hubble Space Telescope and India's AstroSat, astronomers can filter out the older, cooler stars to see these blue beacons. The ultraviolet imaging telescope on board AstroSat has been particularly effective in unmasking the culprits behind the vampirism. In the case of WOCS 9005, AstroSat detected significant UV brightness that could not be explained by the star itself, which has a surface temperature similar to our Sun. Instead, this UV excess was traced to a hot, small companion, a white dwarf that is the remaining husk of the star that was drained to rejuvenate the straggler. This detection of a white dwarf remnant provides the final piece of evidence for the mass transfer model, as the white dwarf is the literal corpse left behind at the scene of the cosmic crime. Observations in the far UV spectrum allow scientists to determine the temperature and age of these remnants, with a companion of WOCS 9005 estimated to have a cooling age of approximately 60 million years. This indicates that the rejuvenation event was a relatively recent occurrence in the history of the cluster. Furthermore, the ultraviolet perspective reveals a menagerie of other exotic objects created by these interactions, including X-ray binaries and millisecond pulsars. By looking through the UV lens, astronomers are essentially conducting interstellar archaeology, digging through the light to find the hidden remains of former star systems. These discoveries confirm that blue stragglers are not solitary anomalies, but are the visible products of a complex and ongoing cycle of interaction and energy exchange. The existence of vampire stars is not merely a stellar curiosity. They play a critical role in the survival of the star clusters themselves. Through a phenomenon known as mass segregation, the most massive stars in a cluster naturally sink toward the center due to gravitational interactions, much like a subway car sorting its commuters. Because blue stragglers are more massive than the average cluster star, they congregate in the core, where they influence the entire system's stability. Once in the core, these massive stars act as kinetic batteries or gravitational egg beaters. As they move through the dense center, they interact with smaller stars, transferring kinetic energy and stirring up the motions of the thousands of neighbors. This constant energy injection helps prevent a process known as core collapse, where the center of a cluster would otherwise become so dense that it could eventually collapse into a massive black hole. By preying on their neighbors and gaining mass, blue stragglers ironically provide the gravitational energy necessary to keep the entire community from falling apart. They are the massive outliers that regulate the dynamics of their cosmic neighborhoods, acting as a buffer against the ultimate collapse of the cluster. This suggests that the vampirism found in these systems is actually a vital part of the ecological balance of the cluster core. The velocities of these stars, as measured by Hubble for nearly 15,000 objects in 47 Tucani, agree perfectly with the predictions of mass segregation. Heavier blue stragglers move more slowly than their lighter neighbors, confirming their status as the dominant gravitational players in the cluster's heart. In this sense, the vampire stars are the engines of the cluster, driving the dynamic evolution and ensuring that these ancient stellar cities remain stable for billions of years. The most nuanced understanding of these stars comes from the discovery of double sequences in clusters like M30. High-resolution images from the Hubble Space Telescope revealed that the blue stragglers in this cluster do not form a single, uniform group. Instead, they are divided into two distinct and parallel tracks on the color magnitude diagram, suggesting they were formed through two completely different processes. The blue sequence in M30 is composed of stars whose characteristics match the models of direct stellar collisions that occurred approximately 1 to 2 billion years ago. These are the products of violent mergers that occurred during a specific period of the cluster's history. The red sequence, on the other hand, consists of stars that are slightly redder and are consistent with binary systems currently undergoing active mass transfer. This separation into two sequences implies that the formation of vampire stars is not always a steady, ongoing process. Instead, it can be triggered by specific dynamical events, such as the core collapse phase of a cluster, which suddenly increases both the collision rate and binary interactions. The discovery of these sequences in M30 and other clusters like NGC 362 shows that the secret of eternal youth is often a response to extreme environmental pressure. When a cluster reaches a state of maximum density, more stars are forced into the vampiric path to survive or emerged by the sheer force of gravity. This tells us that the population of blue stragglers we see today is a fossil record of the most chaotic moments in the cluster's past. By studying these parallel sequences, astronomers can reconstruct the history of the cluster's core, proving that dynamical processes are just as important as isolated binary evolution in shaping the stars. The study of stars that never age naturally intersects with the work of great scientific thinkers who explore the nature of time and energy. Carl Sagan's star stuff analogy reminds us that we are the descendants of stellar death, as every atom in our bodies was forged in the hearts of stars that lived and died billions of years ago. Blue stragglers represent a temporary cheating of this cycle, a way for matter to remain organized and luminous against the relentless pull of entropy. Stephen Hawking's work on black hole thermodynamics offers a profound parallel to the lives of these stars. Hawking's area theorem states that the event horizon of a black hole can only grow, never shrink, which is a gravitational expression of the second law of thermodynamics. Entropy always increases. Blue stragglers appear to decrease entropy locally by becoming hotter and more ordered, but they do so by accelerating the entropy of their companions, which are reduced to dead remnants. Hawking's inquiry into the arrow of time is perfectly encapsulated in these stars, which often look like tourists from the future, objects that appear young in a world that is demonstrably old. Time, as Hawking and Brian Cox have noted, flows in one direction, from order to disorder, and the blue stragglers are localized protests against this inevitable flow. They represent the inherent resilience of matter to maintain complexity, even in a universe that is cooling toward a state of maximum disorder. This connection between the microscopic laws of physics and the macroscopic life of stars highlights our universal link to the cosmos. As we look at these rejuvenated stars, we are seeing the same principles of energy conservation and thermodynamics that govern our own lives on Earth. The arrow of time may be inescapable, but the blue stragglers show that the journey can be delayed and the light can be reclaimed, if only for a few billion more years. Energy scales and the future of civilizations. To put the energy of these vampire stars into perspective, physicists like Michio Kaku use the Kardashev scale, which ranks civilizations based on their ability to harness energy. A Type 2 civilization would be capable of harnessing the entire energy output of its star, perhaps using structures like Dyson spheres to capture every photon. In a sense, a blue straggle is a Type 2 star, a natural system that has learned to harness the energy of another star to prolong its existence. Kaku suggests that while humans are currently a Type 0 civilization relying on fossil fuels and dead plants, we are on a path toward mastering the energies that stars manipulate naturally. The rejuvenation of a blue straggler is a cosmic-scale engineering feat achieved by gravity alone, a process that Kaku identifies as the key to a civilization becoming truly immortal. By studying these stars, we are observing the upper limits of what is possible when energy is transferred between celestial bodies. A Type 3 civilization would go even further, harnessing the energy of an entire galaxy, while a Type 4 could potentially survive the end of the star-forming era by manipulating dark energy. The blue stragglers serve as a natural prototype for these advanced energy harnessing systems, showing how a system can reset its evolutionary clock by siphoning or merging mass. Kaku's vision of the future often draws on these godlike powers that are already present in the physics of the stars. The more we know about these processes, the faster our own knowledge expansion becomes, a principle that Kaku notes has allowed modern civilization to grow exponentially in the last 200 years. The starlifting and rejuvenation seen in blue stragglers might one day be an astro-engineering project for our descendants, allowing them to extend the life of our own sun or create new low-mass stars to house future generations. In this context, the vampire stars are not just anomalies, but beacons of technological possibility. The age of starlight and the heat death of the universe, the ultimate fate of all stars, including the rejuvenated vampires, is tied to what Professor Brian Cox describes as the age of starlight. We currently live in a rich era of complexity and light, but it is a temporary one. Cox has described a future where the universe runs out of the raw hydrogen gas needed to form new stars, and in approximately 100 trillion years, the last star will burn out, plunging the cosmos into eternal night. During this twilight era, the blue stragglers will have long since faded, and the universe will be a dark void populated only by white dwarfs, neutron stars, and black holes. Eventually, even these remnants will change. White dwarfs will cool to become black dwarfs, dense, cold cinders of matter that Cox calls the ashes of stars. At this point, the arrow of time effectively ceases to exist because the universe will have reached a state of maximum entropy where nothing happens, and it keeps not happening, forever. This final state, known as heat death, is an era where the cosmos will remain vast, cold, and desolate for the rest of time. The blue stragglers are the final protest of matter against this inevitable darkness, a temporary defiance of the cold that awaits the entire cosmos. Even the most successful cheaters of the clock must eventually succumb to the fundamental laws of thermodynamics that dictate the end of all complexity and light. Cox uses analogies like the rusting of a ship in a desert or the erosion of a sandcastle to illustrate how everything naturally tends from order to disorder. The vampire stars are like a sandcastle that has been temporarily reinforced by new sand, but the tide of entropy is rising and will eventually wash everything away. Our place in the universe is defined by this finite age of starlight, making every observation of these enduring stars a precious glimpse into the resilience of the cosmos. The secret of the vampire stars, the blue stragglers, is a testament to the complexity of a universe that refuses to be simple. By siphoning mass from companions or merging through violent collisions, these stars prove that the actuarial tables of the cosmos can be challenged and that the fate of a star is not always sealed at birth. They are a reminder that in the dense hearts of clusters, as in the history of human life, immortality is often a matter of interaction, connection, and energy exchange. As we look up at the stars, we are seeing a reflection of our own quest for understanding and longevity. Carl Sagan's perspective, that we are star stuff that has attained the ability to understand the universe, reaches its peak when we decipher the chemical barcodes of stars like WOCS 9005. These stars are not just anomalies. They are the dynamical batteries that stabilize their galaxies and the ultraviolet beacons that light the way for future discovery. They teach us that while the age of starlight is finite, the ingenuity of nature to stop the clock is a melody in the cosmic symphony that resonates across the billions of years of our existence. The blue stragglers show us that the universe is not just a place of fading light, but a stage where matter can reclaim its youth and shine with a brilliance that defies time itself. We are part of this story, a brief and conscious expression of the same stardust that is currently fueling the final protests of these vampire stars. In the end, the story of the blue stragglers is our story, a journey of resilience against the inevitable dark. By uncovering their secrets, we are not just doing science, we are fulfilling our destiny as the universe's way of knowing itself. Even as the light eventually fades, the fact that we were here to see it, to understand the vampires of the deep sky, and to trace the arrow of time, is perhaps the greatest wonder of all.